An oscilloscope display presents more information at one time than any other measurement instrument. A scope lets you see and measure many things about a signal source at once, rather than requiring you to make many separate tests. It is this ability to visualize what is happening in an electronic world that makes the oscilloscope such a powerful tool. For example, on an oscilloscope you can see how much of a signal is DC, how much is AC or changing with time, and the waveform period and frequency. If the signal is digital data, we can measure the pulse width, repetition rate, and in general view the shape of the pulses. Many times it's that shape that's important. The oscilloscope displays information by drawing a graph of the input signal versus time. It does it by moving an electron beam across a phosphor coating on the inside face of a cathode ray tube. The result is a brief glow, tracing the path of the beam. Only an electron beam can be moved quickly, easily, and accurately enough to draw graph lines like these in milliseconds, microseconds, or nanoseconds. To explain how an oscilloscope works, we'll divide it into 4 functional blocks. The vertical system supplies the vertical axis of the graph. The vertical system moves the electron beam up or down to draw the graph. The horizontal system controls the left to right movement of the beam. The trigger system determines when the horizontal system starts that movement. The display system contains the cathode ray tube, on which the graph is drawn. The vertical system controls movement in what's called the y-axis. Y signal information is applied through calibrated attenuators and an amplifier called a channel. The vertical system also has position controls and ways of selecting and combining 2 channels. The horizontal system controls horizontal movement, the x-axis. It uses an accurately timed sweep waveform that moves the beam in a constant and linear fashion horizontally across the CRT. This allows time measurements to be made on events applied on the vertical axis. There is also a horizontal position control and a way of connecting vertical channel 2 to the horizontal system for special XY displays. The display system has a Z dimension, which controls trace brightness. It determines whether or not the electron beam is turned on and how bright it is when it is on. The Z-axis is controlled in 3 ways. First, the beam is turned on during the horizontal sweep time. Second, the intensity control gives the operator control of how much it's turned on. And third, there's a Z-axis input on the rear panel for display brightness control by external means. We'll talk in detail about the display system first. The first thing one sees when looking at the CRT is the graticule. It's the grid of lines on the CRT faceplate. The graticule is the reference for your measurements. High-quality oscilloscopes have this graticule on the inside of the faceplate. Though different-sized CRTs may be used, graticules are usually laid out in an 8x10 division pattern. The labeling on scope controls always refers to these major divisions. The tick marks on the center graticule lines represent minor divisions or subdivisions. These help measure features that are fractions of whole divisions in size. Rise time measurements are very common, and most scope graticules include rise time measurement markings, dashed lines for 0 to 100% points, and labeled graticule lines for 10 to 90%. When an oscilloscope is first turned on, the CRT may not show anything. This can happen for several reasons. The beam may be adjusted off-screen by the position controls, or the intensity control may be turned down too far. The beam finder helps to locate the display anytime it's off-screen. When you push the beam find button, the intensity is increased and the vertical and horizontal deflection voltages are reduced, so that the beam always appears on the screen. When you see which quadrant of the screen the beam appears in, You can turn the horizontal and vertical position controls to reposition the trace to center screen. When you release the button, adjust the intensity control for a visible trace. An intensity control is necessary because you use a scope in different ambient light conditions and with many different kinds of signals. A slowly moving spot is brighter than a fast-moving spot. If the spot is always moving fast and repetition rate is low, the intensity must be increased. In another example, the slower-moving horizontal components of square waves will always appear brighter than its faster-moving vertical components. So the intensity control may be adjusted depending on which parts of the waveform you want to see clearly. The scope's electron beam is focused on the CRT faceplate by an electrical element within the tube. The focus control adjusts the grid for optimum trace sharpness. Astigmatism control is a screwdriver control used in conjunction with the focus control to obtain a well-defined display over the entire graticule area, and it does not require readjustment during normal operation of the instrument. The screwdriver slot trace rotation adjustment aligns the horizontal deflection of the trace with the fixed graticule. To avoid accidental misalignments when the scope is in use, the control is recessed. The Earth's magnetic field and other magnetic fields affect trace alignment. When a scope is moved about, as a service scope will be, the trace rotation adjustment can quickly realign it. As we said, the vertical system of a scope displays the y-axis, or vertical information, for the CRT screen graph. To do this, the vertical system accepts input signals, attenuates, amplifies, and combines them to develop y-axis deflection voltages. The display system then uses the deflection voltages to control, deflect, the CRT electron beam in calibrated steps. The vertical system also provides signals to the trigger circuit. The input coupling switch of each vertical channel lets you control how the input signal is coupled to the vertical channel. DC, AC, and ground reference are selectable. DC input coupling connects the signal directly to the amplifier input. It lets you see all electrical components of a signal. AC coupling blocks the constant or DC components with a capacitor and permits only the alternating or AC components to be displayed. The ground position disconnects the input signal from the vertical system and provides a free-running baseline showing the scope's reference ground if the trigger mode is an auto. Using the ground position does not ground the circuit under test. A volts per division switch controls the sensitivity of each vertical channel. Having different sensitivities extends the range of the scope's applications. By using this volts per division switch, most scopes can display signal levels from 5 millivolts or less to 10 volts or more per division. The vertical sensitivities are shown by two areas under the skirts of the volts per division switches. The 1 o'clock area shows the scale factor when you use the standard 10 times probe. The 11 o'clock shows the factor for a 1 times probe or direct connections with a BNC cable. The knob in the center of the volts per division switch provides a variable change in the scale factor. This is useful when you want to make quick amplitude comparisons on several signals. Most scopes have several vertical operating modes controlled by two switches or a series of push buttons, either channel alone and both channels in either the alternate, add, or chop modes. In the chop mode, the scope draws small parts of both waveforms by switching rapidly back and forth between them. At slow sweep speeds, it looks as if there are two beams drawing the waveforms. The alternate mode draws one trace completely, alternates to the other, and draws the second trace. This appears best at the faster sweep speeds where your eyes can't see the alternating trace being drawn. To compare two signals that require slow sweeps, the chop mode is most effective. The 2335 has a unique mode that will automatically select the most useful switching method, alternate or chop, for dual displays. This is selected by pressing both alternate and chop buttons together. The Add mode can be used to add the two signals, channel 1 and 2, or with the Invert switch to subtract them. Differential measurements use the Invert push button to invert channel 2 polarity, and the Add vertical mode to effectively subtract channel 2 from channel 1. When you push the Invert button in, the signal on channel 2 is inverted. When the switch is out, both channels have the same polarity. To draw a graph, the CRT beam needs to be moved horizontally as well as vertically. The horizontal system supplies the second dimension by providing time-related deflection voltages that move the electron beam horizontally. The horizontal system also provides a signal to the Z-axis of the scope, which turns on the electron beam during the horizontal sweep and off during its return or retrace. The horizontal system components consist of the sweep generator and the horizontal amplifier. The sweep generator produces a sawtooth waveform that is processed by an amplifier and applied to the horizontal deflection plates of the CRT. A sawtooth waveform or voltage ramp is produced by the sweep generator. The rising portion of the waveform is called the ramp. The falling edge is the retrace, and the time between ramps is the hold-off time. The sweep of the electron beam across the screen of a scope is controlled by the ramp, and the return of the beam to the left side of the screen takes place during the retrace. The hold-off prevents the sweep from starting before the horizontal system is reset. The linear sweep generator is the unique function that makes the modern oscilloscope possible. Because the rate of rise in the ramp is linear, modern scope time bases can be calibrated in accurate units of time. You can pick time units for observing signals from very short times, measured in nanoseconds or microseconds, or relatively long times of several seconds. Like the vertical system volts per division switch, the time base control's markings refer to the screen scale factors. If the seconds per division setting is 1 millisecond, that means that each horizontal major division represents 1 millisecond, and the total 10 division screen width displays 10 milliseconds. Besides the calibrated speeds, you can vary any sweep speed by pulling out and turning the variable control in the center of the seconds per division switch counterclockwise. This control slows the sweep speed by at least 2.5 to 1, making the slowest sweep 1/2 second times 2.5 or 1.25 seconds per division. Remember that the detent in the extreme clockwise direction, or pushing in on the knob, are the only calibrated positions. The fastest sweep speeds of a scope are available with horizontal magnification. Magnification multiplies the sweep speed by the amount of magnification. On most scopes, the horizontal magnification is by a factor of 10. For example, 0.05 microseconds per division magnified by 10 times is 0.005 microseconds, or 5 nanoseconds per division. The 10 times magnification is useful when you want to examine parts of waveforms in greater detail. The trigger system determines when the oscilloscope starts the trace. This is important because getting time-related information is one of the reasons you use a scope. So each trace should start at the same time. The advantage of a triggered oscilloscope is a stable display. Triggering gives you a stable display because the same trigger point starts the sweep each time. Slope and level controls define the trigger points in the trigger signal. When you look at a repetitive waveform on the screen, you're seeing all those sweeps overlaid into what appears to be one picture. The trigger level and slope controls define the trigger point. The slope control determines whether the trigger point is found on the rising or the falling edge of a signal. The level control determines where on that edge the trigger point occurs. The desired trigger signal source is selected with the source switches. You must also specify the trigger signal coupling: AC, LF reject, HF reject, or DC. The trigger signal source can be selected specifically as one of the vertical channels, or we may let the vertical mode switch select the trigger source. We can also select the power line as the trigger source if it has some time relationship with the displayed signal. We can also select the external trigger input or external trigger attenuated by 10. If the vertical mode switches are set at channel 1 and the trigger source is in vertical mode, then the signal on channel 1 triggers the scope. If you're looking at channel 2, then that channel triggers it. If you switch to the alternate vertical mode, then the scope looks for triggers alternately on the two channels. If the vertical mode is add, then channel 1 and channel 2 is the triggering signal. In the chop vertical mode, the scope trigger source must be in any other position besides vertical mode to prevent the instrument from triggering on the chop frequency instead of your signals. Just as you may pick either AC or DC coupling when you connect an input signal to your scope's vertical system, you can select the kind of coupling you need when you connect a trigger signal to the trigger system's circuits. For internal and external trigger signals, you have a choice of AC coupling, DC coupling, LF reject, which rejects the low-frequency components of the input signal, or HF reject, which rejects the high-frequency components. Triggering on the displayed signal has the obvious advantage of letting you see where you're triggering. But that isn't always what you need, so external triggering is also available. External triggering is often useful in digital design and repair. There, you might want to look at a long train of very similar pulses while triggering with an external clock or word trigger. Not every trigger event can be accepted as a trigger. The trigger system will not recognize a trigger during the sweep or the retrace, and for a short time afterward called the hold-off period. The retrace is the time it takes the electron beam to return to the left side of the screen to start another sweep. The hold-off period provides additional time beyond the retrace that is used to ensure that the display is stable when it starts again. Sometimes the normal hold-off period isn't long enough. When the trigger signal is a complex waveform with two or more possible trigger points before the waveform repeats, a simple trigger will result in an alternating series of waveforms on the screen instead of the same waveform each time. Digital pulse trains are a good example. Each pulse amplitude is very much like any other, so there are many possible trigger points, not all of which result in the same display. The variable sweep hold-off control provides the ability to control when a trigger point is accepted by extending the hold-off to the point where the waveform repeats. The trigger circuit has three operating modes: normal, automatic, and single sweep. In the normal mode, the range of the trigger level control includes any on-screen voltage. When there is no triggering signal present, there is no trace on screen. In the 2335, the auto mode supplies a bright baseline if there isn't any trigger signal or the trigger signal has a less than 10 Hz repetition rate. In the single sweep mode, pressing in on the spring return push button momentarily arms the A-sweep circuit for a single sweep display. This mode operates the same as normal, except only one sweep is displayed for each trigger signal. Another single sweep cannot be displayed until the single sweep push button is momentarily pressed in again to reset the A-sweep circuit. This mode is useful for displaying and photographing non-repetitive signals. Delaying time-based scopes like the 2335 let you select either of two sweeps, A-sweep and B-sweep. The A-sweep starts immediately after a trigger, while the B-sweep is started after a controlled delay time, a precise amount of time between the trigger point and the beginning of the display. In delaying time-based instruments, one sweep is triggered in the normal fashion, and the start of a second sweep is delayed by a measured portion of the first. To keep these two sweeps distinct when describing them, the delaying sweep is called the A sweep. The delayed sweep is called the B sweep. The length of time between the start of the A sweep and the start of the B sweep is called the delay time. Delayed time-based scopes provide an intensified zone on the A sweep. This intensified area helps you use the delayed sweep as a positionable magnifier. Trigger the A sweep normally, then select the scope's intensified horizontal mode. Now the signal on the screen will show a brighter zone, representing the B sweep, after the delay time. With the delay time multiplier, move the delay time, the intensified zone, so that it begins at the part of the signal that interests you. Then switch to the B delayed mode and increase the B sweep speed to magnify the selected waveform portion so that you can examine it in detail. The B delay time position dial makes timing measurements to 1.5% accuracy. To do this, select the intensified horizontal operating mode. Place the intensified zone over the signal to be measured. Push B and position the B sweep waveform where the timing measurement is to begin, and note the B delay time position dial setting. Move the dial to where the measurement ends and note the reading there. Subtract the first reading from the second and multiply by the A sweep seconds per division setting. This mode is typically called runs after delay. The 2336 oscilloscope delayed sweep operation is the same as the 2335, except for the B trigger controls and liquid crystal readout in the front panel cover. The 2336 B sweep has three triggering modes: delta time, runs after delay, and triggerable after delay. In the triggerable after delay mode, the delay time is selected by the B delay time position control. The B sweep is triggered after this time when a trigger is present. The trigger source can be the vertical mode switch setting, channel 1, channel 2, or an external trigger. This mode is useful when the signal to be viewed on the B sweep has time jitter on it, relative to the A sweep trigger. Calibrated delayed sweep measurements are made using the delta time mode. With this mode, the A sweep has not one but two intensified zones. These indicate the positions of two alternating delayed B sweeps. Use these two intensified zones to select the time events to be measured. Select the B sweep display and superimpose the two events, or position both events at the same vertical graticule line. The time difference between the two events is then read from the liquid crystal display. Even the units of measure are displayed in seconds, milliseconds, or microseconds. This delayed sweep measurement method removes many error sources, such as misreading delay time dials or the A sweep speed, or making subtraction errors. If you have questions about operating the 2335 or 2336, consult the operator's manual. The manual also contains many measurement and application tips.